So my dear student, colleagues and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar, and I'm happy to share with you all that it's our 64th International Physics webinar. So good afternoon to all, and hope you are well and safe from Corona pandemic. So all we know that we are living in a Corona pandemic situation. So we know that the most devastating epidemic of 21st century is the coronavirus of COVID-19. So all the institutions have been shut down due to coronavirus from March 2020. So we cannot continue our normal academic program inside the campus. So we have to start our online program to continue our academic program. So I think you have already come to know that our Department of Physics has started its online program, including the online classes and online international physics webinar. So we are trying to adjust with this new normal situation, and I think we have already completed our 63rd, and we're trying to make an environment for our students so that they can feel that they are in touch with studies. So today is very important day for our department, as we are going to witness a very good webinar with such a one of the best scientists from Netherlands. And today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Leiden Institute of Physics, Lorentz Institute, Leiden University, Netherlands, in gravitational waves, astronomy, and black hole. And we have with us here today Dr. Subodh Patil, sir. He's currently working as an assistant professor at the Leiden Institute of Physics, at Lorentz Institute, at the Leiden University in Netherlands, and he has already connected with us. So I'd like to welcome our speaker, sir. So good afternoon and welcome to our International Physics webinar, and welcome to Bangladesh and our university. And thanks for accepting our invitation, sir.
No, thank you very much for the invitation. And before I continue, I would just like to point out that I think this is a fantastic thing that you're doing, and I think it's a really great idea, actually. In a time like this, it's actually to me, it's surprising that it hasn't occurred to people and the community overall before, that one can always invite speakers. One is much more able to invite speakers from anywhere, really remotely. And so this is a fantastic way for people like me to interact with students I wouldn't normally get to interact with myself. So this is a great idea, and I'm very happy to be participating.
Thanks, sir. So thanks for accepting our invitation, sir, and we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. The main aim of our program is to motivate and encourage our students in this Corona pandemic situation, sir. So you can start your session. So thanks again.
Yep. So I'm going to talk to you today about primordial black holes. And if you've never heard of them before, or if you have heard of them before, it's a topic that has actually become quite topical. It's become, a lot of people become interested in it again. This idea goes back actually, I think now almost 50 years. But recently, it's come back into the minds of astronomers and astrophysicists and cosmologists because, as of about a little over almost 4 years ago now, it was announced that the LIGO collaboration had seen gravitational waves for the first time. And what they had actually seen was consistent with the merger of two black holes, approximately 1 megaparsec away. So what was the exact? I think a megaparsec away, right? And the masses of these black holes was of about 30 solar masses. So what happened is, in some distance away, these two black holes were in an orbit, and they radiated their way through gravitational radiation, and then they merged. And this is the signal that people had thought that they had seen. Now, immediately there was a mystery, which is the masses for these black holes is a bit strange. Actually, it's very challenging to imagine where black holes of such masses could have come from. And this immediately led a group based out of Johns Hopkins University in the United States to propose that maybe what LIGO saw was actually seeing a population of black holes that could constitute dark matter. So dark matter is this unknown component of the matter density of our universe, and we have very little idea of what it is. It could be microscopic, it could be particles, it could be objects that are quite macroscopic. In fact, they could even be planets or something that somehow just don't interact with us electromagnetically. And so primordial black holes could people thought, these authors proposed that maybe what LIGO had seen is actually not just the merger of black holes, but that these black holes were created, if you like, not from stellar collapse, but right after the Big Bang, and that this is the dominant component of dark matter. So it seems like a lot of ideas tied together at once. So let me unpack that for you for a bit. The mystery is, where do black holes of these masses come from? There's another mystery. What is dark matter? So these authors thought maybe the two things have to do with each other, and that what LIGO had seen is actually evidence that these black holes are indeed primordial, and in fact they are dark matter. So this idea led a whole burst of interest in the community of people trying to understand and work out its consequences in more detail. So what we are seeing is, so if you like, what happens over the life cycle of a usual star. Stars, exist in a range of masses, and this has to do with the environments in which they were formed. And once a star runs out of nuclear fuel, it can undergo a various set of processes that will end up in some remnant object. If they are below a certain mass, they will end up in so-called neutron stars. And so this is basically the densest form of matter that we are aware of that's consistent with our standard model that one could form. And if the masses of these stars are greater than a particular mass, then they end up collapsing into an object called a black hole. And these black holes, they don't just sort of hang around in the universe. They're sort of floating around, and sometimes they end up in an orbit. They can find each other and end up in a binary orbit, and then merge and form more massive black holes. So in this slide, what you're seeing is sort of a pictogram of the different range of black holes that that LIGO thinks it has seen so far. So there are black holes that one can see in X-rays. These are so-called X-ray binary black holes, which means that as matter is falling into them, they sort of emit X-rays, which we can see through electromagnetism. And what we're seeing is that there are black holes that are formed, and then some of them can merge into bigger ones, and that's what this pictogram is demonstrating. And so, in order to understand, the different, if you like, zoo of black holes there are in the universe, there are the usual stellar black holes. So by stellar black holes, it refers to black holes that are formed as the end product of the life cycle of a typical star or an atypical star even. And these tend to be produced up to black holes of up to about 20 solar masses, so 20 times the mass of the sun. So, and there's various ways in which these could be formed. But the main channel, if you like, is when a typical star is formed. So something like our sun, for instance, would be on the top part of this pictogram. And as the sun runs out of nuclear fuel, it'll eventually blow up into a red giant, and then the red giant will throw off all of its matter once it finally runs out of nuclear fuel, and the end product will be a white dwarf. So our sun will not end up as a black hole; it's too light. But for more massive stars, they can end up as supergiants that once they run out of nuclear fuel, there's a catastrophic event that happens that results in a supernova. You may have heard of these things. And depending on their mass, they either end up as a neutron star or a black hole. And because there's a bound on how massive stars can be, there's also a bound on how massive black holes you could form from the collapse of stars. And this is about 20 solar masses. And note that 20 is this is about, quite a bit lighter than 36, which is sort of the mass of the black hole that LIGO thinks it's seen. There's other ways to form black holes. And there's this hypothesized type of object called a quasi-star, which isn't powered by nuclear fuel, but it existed early in the universe's history. when, if you like, there was a sort of a gravitational seed around which matter just started falling in really hard, really fast, and then it's the matter infalling that's releasing radiation that's actually causing the thing to shine. And once the central black hole forms there inside one of these objects, they accrete more and more matter, and you can end up producing black holes of thousands of solar masses. So between 1,000 to 10,000 solar masses. And these are known as sort of intermediate mass black holes. And we see evidence for them as well. And then there's a very peculiar type of object, which is a mystery as to how they formed. We really don't have any good ideas as to how they're formed, but we know that basically about at the center of every large galaxy, they are the anchor, the gravitational anchor around which the galaxy is. All the stars in the galaxy are rotating. So, for instance, at the center of our Milky Way, we believe that there is a supermassive black hole with a mass of about 1 billion times the mass of the sun. And exactly how these objects are formed, we really we have ideas, but none of them are completely convincing at this point. So, all of these different sort of types of black holes that we've seen, there is a gap. There's a sort of a mass gap in the population of black holes. If we did a census of black holes, right? So, if we did like we do a census of our countries and we see people, we count the ones that are out there. If we did a census of black holes, we find that there's actually a missing range, or we expect the population to thin out drastically in the range of between 30 and 60 solar masses. But this is precisely the range in which LIGO keeps seeing these black holes. So this begs the question, where did these black holes come from? And what this caused was the community realized that maybe it's time to revive an idea that was actually proposed in the 60s by the Soviet physicists Zeldovich and Igor Novikov. And what they realized was that maybe in the very early universe, and before the cosmic microwave background, even before, if you like, the remnant radiation from the Big Bang decoupled from matter, that gravitational seeds could have that there could have been large enough fluctuations in the early universe that collapsed in on themselves and formed black holes. And so the idea that black holes could have been around without any stellar mechanism to form them was first proposed in this paper in the 60s. And so the question, the observation that LIGO has seen black holes with masses that are very hard to produce via astrophysically has led people to the very natural conclusion, maybe these black holes have always been around. Maybe they're around, right after the Big Bang. And such black holes are referred to as primordial. And so therefore, the question is, could these black holes have been primordial in origin? And the most interesting piece of evidence, although the evidence up till this point is still quite marginal because it's very difficult for us to actually determine the spins of the black holes that ended up, merging to form a bigger black hole with LIGO, because there's too much degeneracy in the different parameters when we try to do a template fitting to the observation. But what we're seeing is certainly consistent with no spin. So if you imagine, the collapse of matter to form a black hole, it's actually very hard to produce something with no spin because of conservation of angular momentum, right? In order for something to have no spin as you collapse, things have to basically, come in with basically zero impact parameter, and so this is very hard to produce astrophysically. A typical astrophysical black hole will be spinning. And so what LIGO has seen is also consistent with no spin, but it certainly doesn't rule out that they have a spin, but it's just circumstantial evidence to add fuel to the fire, if you like. So these black holes have no spin, and so this is starting to look maybe more like we should take this idea very seriously. And the thing about black holes that are primordial is that since they weren't formed by stellar collapse, they could actually exist with a range of masses, much lighter than the mass of the sun, quite a lot much more lighter, in fact. And they can be, in fact, so light that a process known as Hawking evaporation might even kick in. So Stephen Hawking his name will appear again in this talk a little later. His name is all over this subject. Realized that in fact black holes, in his own words, the black holes ain't so black. Okay, so they don't just absorb matter and then emit nothing. They in fact emit thermal radiation, and the reason for that is quantum mechanics. And a very intuitive way to understand, what is causing Hawking radiation is the idea is that every black hole has an event horizon beyond which nothing can escape. Even if you fired it out at the speed of light, nothing can escape. And according to quantum mechanics, according to Heisenberg's uncertainty principle, there's no such thing as a vacuum. There's always particles appearing and disappearing again in the vacuum in a process of virtual creation and destruction. If you ever go on to take quantum mechanics, or if you have, this might seem familiar to you, or you learn about it. And the idea is that at the edge of an event horizon, if there is a virtual pair of particles produced, then if one of them is above and one of them is below the event horizon, one of them will escape and the other one doesn't. And that's the radiation. That is Hawking radiation. And it's a very cartoon picture. What I explained, the actual details are a bit more different, but it's useful. It's a useful way to understand how black holes can actually emit particles. And this is how the black hole loses its energy, and it basically ends up radiating away. For a black hole, and the rate at which it radiates away is proportional to its mass. So you can go away and calculate the lifetime of a black hole, and it's given by this formula here. 10 to the 67 years is a very, very long time. Our universe has only been around for 13 billion years, so it's 10 to the 10. So this is really, really, really immense time scale. But if the mass of the black hole is so much smaller than the mass of the sun, it could evaporate potentially before the lifetime of the universe. And so it turns out that that black holes with masses of a slightly, of more than 10 to the 14 grams, so that's 100 trillion grams, could still be around. And those that were lighter would have evaporated away, if you like. But that's still very, very light, right? It's still 10 to the minus 19 times the mass of the sun. So that's the mass of the sun is about 10 to the 33 kilograms. So this is about 10 to the 14 grams, or about 10 to the 11 kilograms. So it's quite a lot lighter than the Earth. And so the idea is that these objects could still be around and could be populating the universe with a population of black holes that we have never we wouldn't know about otherwise. And if we ever see in LIGO or any gravitational wave observation evidence that there was a black hole with a mass of less than 1.4 times the mass of the sun, then we know, in fact, that there's no astrophysical process that could have produced it, because it's below this limit called the Chandrasekhar limit. So Chandrasekhar realized actually that that black hole, that any stellar object below this mass is just too light to collapse into a black hole, if you like. It would turn into a neutron star instead, or a white dwarf rather. So any time we will ever see, if any gravitational wave observation ever sees a black hole lighter than about the mass of the sun, 1.4 times the mass of the sun, we know for sure it was produced primordial. It would be spectacular evidence. It would be smoking gun evidence that they were formed not in a stellar process, perhaps through some unknown process, of which the most natural candidate is that they are primordial. So we should, at this point, I'd like to sort of explain to you how these objects could have formed. So one of the most surprising things to people, to students, when they're first learning general relativity, or after they've learned general relativity, which I hope one day you'll get to study, if you haven't already, is that the intuitive idea of a black hole is that a black hole is an object that forms when you pack enough matter into it, into a small enough region that not even light can escape. And then it's a very, very, very singular evidence. It's a very singular occurrence in terms of the processes that can happen in the universe. One of the most surprising things is that you can also form black holes in the absence of any matter. And the reason for that is gravity isn't so much of a force as it is a distortion in space-time, in the fabric of space-time. And every material object that you put in to space-time distorts the fabric around it, and everything else is just trying to move in a straight line. But because space-time is curved, things move in a curved path. So the way to think of the orbit of the Earth, if you like, around the sun, is that the sun is this very heavy ball in the middle of an elastic fabric, and the Earth is just moving around in what is trying to do a straight path around what is a curved geometry. In order to visualize this geometry, it's a bit more difficult because the curvature is mostly in the time direction. So you have to have this sort of a space-time image of it. But nevertheless, it's a useful way to build up intuition. And so black holes can be formed in a variety of ways through large enough shocks in the fabric of space-time. And one of the ways it can be produced is in this thing called bubble collisions that could have happened in the early universe through this thing called a first-order phase transition, which you've known about since you were a kid, if you've ever looked at water being boiled. Because what you're looking at when you see a pot of water being boiled is precisely a first-order phase transition. There are bubbles being created in the water being boiled, and sometimes these bubbles find each other and they collide. So what is actually happening inside that water is that once you raise the temperature of water above a certain temperature, about 100 degrees at atmospheric pressure, it becomes energetically favorable for water to exist in a phase that has lower energy, and that is gas, right? A lower free energy. And so water tries to form this lower energy phase, which is gas, but then there's a competition because as it tries to form this phase, it's surrounded by water, and so there's a surface tension that's trying to make it collapse again. This bubble has to reach above a critical size at which the volume effect beats the surface area effect, and then the bubble condenses. And then as these bubbles condense, they can find each other and collapse and collide. And so this also happens in the early universe in different phases of the stuff that makes up the standard model. It's a bit more abstract, but the physics is identical. And so the idea is that when phases of true vacuum find each other, that they can collide, and these bubble wall collisions can be so violent that they can create shocks in space-time so violent that they themselves create black holes. It's a bit. So this is in the same spirit as a phase transition. Sometimes you don't form bubbles, but sometimes you form vortices. So in fact, superconductors often exist in these phases where you have different vortices instead of bubbles, if you like, forming of true vacuum. And these vortices can often sometimes find each other and collapse and form loops, and this can also form black holes in the early universe. Now, there's another mechanism that is actually related to something that is you can even see with your eyes when you look out far enough, which is when we look out into the universe, what we see is galaxies. Well, we see primarily our own galaxy, and then we see planets, and then we see these clouds, and these are other galaxies. And if we looked at the large-scale structure of the universe, we see that there's this filamentary structure of the largest scales of how the galaxies all form. That's just the structure of visible matter in the universe. And so how did that come to be? Well, it comes from some seed perturbations that existed in the early universe, these gravitational seeds, gravity is an attractive force, so once you have more stuff appearing somewhere, more and more stuff finds it, and things collapse. And what we're seeing in the sky, this cosmic filament, is, if you like, the structures that formed around some primordial perturbations, some primordial fluctuations, whose origins we think come from a phase before the Big Bang called inflation. We don't need to worry about it too much, but for the purposes of this talk, you just need to remember that what we're seeing around us is the process of gravitational collapse set up by some initial conditions at the Big Bang, which were these sort of seed fluctuations. And what Stephen Hawking realized, actually, is that maybe the same thing that's producing these little fluctuations, if some of the fluctuations were so big, if at some point the fluctuations were just so large, maybe these fluctuations themselves could have collapsed into black holes. And so it's actually a very beautiful idea. What Stephen Hawking proposed is the same thing that's causing the structure of galaxies that we see at different scales is actually causing the gravitational capacity so much that it's actually causing black holes to appear as well. And so he proposed that maybe the origins of these primordial black holes has the same origins as the thing that provided the structure of our galaxies. And so this is the basic idea of and this is the dominant mechanism through which most people entertain how primordial black holes are formed. Certainly, it's the most straightforward way in which we can generate these primordial black holes. So at the background of this slide, you will see this sort of blue and red sort of picture, and it's actually a map of the cosmic microwave background. And if you've never heard of it, the cosmic microwave background is the relic radiation left over from the Big Bang. And what does that mean? At some point in the early universe, the universe was so hot and dense that light could never really travel very far. It kept scattering off of matter, right? So and then at some point, and the reason it kept doing that was because there were free electrons, right? So there was protons, there's electrons, everything. There was just a plasma. It was a very charged plasma, and light kept scattering off of these things, and so it was sort of doing a mean free path. Nothing could travel in a straight line. But then when the universe cooled enough, hydrogen could form. And so electrons and protons found each other, and then everything became neutral. And then all of a sudden, light could no longer scatter so easily for things that just traveled in a straight line. That moment is known as recombination. And that moment is what we see in this picture in the background. It's the moment at which light suddenly started to free stream. It suddenly broke free. And there's actually a thing you may have experienced yourselves that actually approximates this very moment. In the early morning, sometimes when you're walking through a field or sometimes, and it's very misty, right? And you can't see, there's light, it's bright. So you can definitely see that there's light around, but you can't see objects past a certain distance because light keeps scattering around and there's no visibility. But the minute, the temperature sort of, changes enough such that the mist clears, then suddenly light can travel, right? And then you see everything around you. You can see the field. So that's exactly a moment that happened in the early universe, and that moment is what we're seeing in this background picture. And what we're seeing is something very, very remarkable. We're seeing the fact that no matter which direction you look in the universe, it looks the same. There's this picture is color coded. There's some parts that are red and some parts that are blue, and that's telling you where the light is, if you like, hotter or colder coming from in different directions. And it's a color coded plot, and it's very exaggerated. The color coding is there to bring out the fact that these fluctuations are to, in fact, 1 part in 100,000. So everywhere you look, you're looking at radiation coming at you from the Big Bang that is the same temperature, up to fluctuations in 1 part in 100,000. And so that's something that's a prediction, in fact, of the Big Bang, that we should see if you like, a perfect temperature everywhere we look around. But these fluctuations that we're seeing are telling you that the different locations you're looking at, the photons had a different history. In some places, they had to climb out of a bigger gravitational well, potential well. Okay, so if you like, because of very crudely, Einstein's, if you like, most famous equation, E equals mc squared. The more you climb out of a gravitational potential, that has to cost you energy. And so photons that were coming from a deeper gravitational potential had to expend more energy to climb out of it, just like you have to spend more energy climbing out of a well or climbing up a ladder. And in doing that, they've lost energy. And when a photon loses energy, it becomes redder. So what we're seeing in this map is, in fact, a map, if you like, of the topography of the gravitational potential in the early universe. And it's really, really remarkable because we're actually seeing the beginnings of the primordial seeds, the little fluctuations that went on to form the galaxies that we end up seeing. And so what Stephen Hawking proposed is that, in fact, we're limited in scale as to what we can see in the cosmic microwave background, that perhaps at very, very tiny scales that we can't resolve in our observation so far, that maybe some of these fluctuations were so big that black holes formed out of them. Okay? And so therefore, by looking at other ways to look at the structure of the universe at very, very small scales, we could actually be probing whether primordial black holes were indeed formed. Or if you like, the existence of primordial black holes could tell us about structure at very, very small scales in the universe. So to make this a little bit more sort of concrete, what this picture is showing you, by the way, in the background, is the time-forwarded is the result of these seed fluctuations you're seeing in the cosmic microwave background, fast forwarded to today. Okay, so if we looked as far out as we can see, okay, way further than the galaxies that we see around us in our local group, we looked as far. So if you imagine the boundaries of this oval are the edge of the visible universe. This is what the universe looks like. Okay, our galaxy wouldn't even be I mean, it's even microscopic. It's not even a pixel in this. It's not even maybe even a tiny fraction of a pixel, right? I mean, these are clusters, and so this is what we see when we look out at the universe at the largest scales, and what we're seeing is the product of those seed fluctuations we saw in the cosmic microwave background, just evolved forwards in time just by pure gravitational collapse. So those fluctuations that we saw in the early universe that had a very specific statistical property, which is that there's no evidence that that the fluctuations, if we looked at their Fourier decomposition, that any Fourier mode was louder than any other. If you just wait long enough, the scale invariance of that transforms into a structure of the clusters of galaxies that very, very accurately approximates what we see in our universe today. And so to just give you a sense of scale, our own galaxy is about 80 kiloparsecs across. So in this plot, it really would be a pixel. So this is how you go from seed gravitational potentials in the early universe into the large scale structure that we see today. And so so this begs the question, what is the origin of these primordial fluctuations? Where did they come from? And so the idea is that what we're seeing in the structure of galaxies. So here in this, I don't know if you can see my cursor over here. This is, if you like, actual data from the Sloan Digital Sky Survey, which is mapping, the clusters out to about redshift of I think can't really tell, but it's certainly less than 1. But this is, if you look out, our observations actually see this sort of filamentary structure of the galaxies that we see around us. And the idea is that these initial fluctuations we saw in the cosmic microwave background then evolve into something like this. But where did these fluctuations themselves come from? And the idea is, our best working theory is that they are sourced by quantum fluctuations in the very early universe. Sourced by the field itself, we think it's this field called the inflaton field, that gave rise to the Big Bang. So a lightning overview of what inflation is. The Big Bang was set up as the end product of a process in which there was a field there's a quantum field in the early universe that caused the universe to expand really rapidly and stretch in every direction, which is why everything looks the same in every direction. And once that field ran out of energy, it dumped all of its energy into radiation, and that's the Big Bang. And of course, in any quantum system, there's always little quantum fluctuation. So this field had little quantum fluctuations here, and these quantum fluctuations then got imprinted into little fluctuations in the geometry. And then those fluctuations in geometry imprinted into fluctuations in the temperature of photons coming out of that geometry. And that is basically a map of what the gravitational potential was, through which much, much later times, we actually had matter fall into, cold dark matter, and that formed the scaffolding around which the galaxies that we see today are formed. So that's a lightning overview of the origin of these primordial overdensities. And so this is perhaps getting into something a bit more technical. So when I was preparing this talk, I understand that the level of the audience might range from undergraduate to masters, but I didn't want to shy away from certain technical details for some people who may be interested in them. If that's you, I hope you will enjoy the next few slides. If that's not, please don't worry. Just focus on my word. I will talk you through this. Okay. So the idea is that there are quantum fluctuations in the early universe that went on to then source fluctuations in geometry that we then see in the cosmic microwave background. And the idea is that's so. In order to understand how primordial black holes are formed, we should just take a quick detour to understand how these fluctuations actually could exist. And so general relativity, the theory of gravity, is, again, I emphasize, if these equations mean nothing to you, please just follow my words. The theory of gravity is a theory of how matter deforms geometry and how that geometry evolves. And so the idea is that there's a fluctuating matter field in the early universe, that's causing fluctuations in geometry. And general relativity is a theory like electromagnetism. In fact, it's exactly like electromagnetism in a way that we've only started to understand, in the last 30, 40 years, is a type of a theory called a gauge theory. It's the type of theory that exists that's causing, that is responsible for the structure of the standard model of particle physics. And what that means is that there's a degree of freedom which mediates the force. For gravity, it's a graviton. For electromagnetism, it's a photon. And that theory has a gauge invariance, if you like. There's a potential, if you like, that's for it. And there's a big redundancy in your description. And it's a way of encoding the internal symmetries of the theory. So in general relativity, in the theory of gravity, what that's telling you is that space-time doesn't care how you try to describe it in terms of a coordinate system. And that makes perfect sense, right? So why should nature care about how a human being writes something down? It shouldn't. And so general relativity allows us to make that freedom. If you have a space-time in which you have a field and it has some fluctuations, you are completely entitled to describe it in terms of a different description of space-time, where instead of foliating time to go in one way, you can write down another time coordinate that looks like it's slightly different than the other one. But this new time coordinate is such that you basically suck up the fluctuation in the field, and you can arrange it such that the field doesn't fluctuate on this new time slicing. So basically, you've changed the clock from being your original clock to this field phi itself. And so the question becomes, where do these fluctuations go? They become a part of the metric. They become a part of the thing that is fluctuating, the actual distortion of space-time itself, mediated by this thing called the graviton. And these fluctuations are the very thing that we then go on and see in the cosmic microwave background. And so cosmologists love to look at things called correlation functions, which is whenever you see something, right? Whenever you see an object, you can just see, well, how does it vary if I take its value at one point versus another point and then look at it at a different point? That thing is called a two-point correlation function. And that two-point correlation function, that's a function of fluctuating quantum fields, very directly maps into temperature fluctuations in different parts of the sky. And the mapping is quite complicated. We don't need to get into it, but the details are such that we have fluctuations in the early universe, of which there's a two-dimensional snapshot happening in this picture. And the details are and what we see in this snapshot responds to not just the geometry of the universe, but cosmic evolution. And what we're seeing in the cosmic microwave background is we're sampling the underlying two-point function. We're not measuring it, we're sampling it. And so the net result of this is that if we assume that in many quantum processes where there's no preference for any scale, that if there is a physical process that is almost time invariant, then the two-point function, when you look at its Fourier transform, it basically looks like it has no preference for scale. If you just let that initial perturbation evolve in time, it'll end up explaining the fluctuations we see in the cosmic microwave background. So what is this plot showing here? Okay, if you've ever seen a spectrograph of a musical instrument, let's say a violin. Okay, so let's say I took a violin and I played a note, let's say middle A. Okay, so then it's a one-dimensional time series, right? So then I'll hear the main note A, which is at 440 hertz. It peaks at 440 hertz, but then also it'll peak at every harmonic, which is double 440. It's some power of 2 times 440, so 880, 440 times 4, et cetera, et cetera. And these are what these peaks are when you decompose the note from a violin in terms of its frequencies. But then there's all these other frequencies present too. They're much, much quieter. Okay, so the decibel scale is logarithmic scale. Okay, so this is actually 6 orders of magnitude smaller than it's much, much quieter. But nevertheless, when you hear the sound of a violin, when your ear hears the sound of a violin, it's hearing all of these different frequencies, but with these frequencies being louder than the others. Now, actual sound that we're seeing in that you're hearing in your ear right now is a one-dimensional longitudinal excitation. What we're seeing in the cosmic microwave background is a vibration of a two-dimensional surface. Okay, so so we do the same thing as we would do. So what we're seeing here is, if you like, a Fourier transform of the notes of a violin. We can do the same thing to the vibrations we're seeing in the sky. And it's on a two-dimensional surface of last scattering, and we decompose them not in terms of simple harmonic, in terms of sines and cosines. We decompose them in terms of spherical harmonics. If you like, they're the vibrational modes of a sphere. And again, we see that there's some notes. So what would happen if we had something that with no preference of scale in the early universe is cosmic history would then process that into something that looks like this, right? We'd see a very, very loud note here, which is telling us the size of the cosmic horizon. We would see these little harmonics. And this is actually, in fact, telling us what the material properties of the early universe were. So just like I could blindfold you, I could put you in a room, I could blindfold you, and I could play a violin, and you would immediately say, that's a violin, right? You don't need to see the object to understand what it is. Just by hearing something, you can tell what the object is, okay? And this is exactly what we're doing here, just by observing the acoustic vibrations, okay? So the cosmic microwave background is a snapshot of acoustic vibrations. It really is an ultrasound of the universe when it was a baby. And by looking at those vibrations, we can tell about the material properties of the thing, what its speed of sound is, what its geometry is, just like you can implicitly in your ears with a violin. And so this is what's responsible for the structure of galaxies that we see around us. Fast forward in time. And so the idea is, what if, okay, so you see what we're seeing in the cosmic microwave background only samples a very small number of modes down here. Okay, so the modes down here are what we're seeing in this plot over here. So we're seeing no evidence for scale over here. But there's modes that are, if you like, they're very, very high frequencies that the cosmic microwave background is blind to. It's just we don't have resolution to see them. And in fact, there's all sorts of diffusion processes that make it impossible for us to see. But if we look at the structure of galaxies, we could get some evidence for these modes at frequencies that are much higher than what we see in the CMB, but still, not good enough. And so the idea is, what Hawking's idea was what if there was some mechanism that dialed up the mechanism that generated these primordial fluctuations to be very, very loud at very, very small scales, then maybe they could have they could have collapsed and formed primordial black holes. And of course, there's any number of other ways in which we can also go looking for them. They involve looking at distortions of the microwave background from being a perfect black body. They involve gravitational wave observations. We don't need to get into the details, but we're looking for ways in which we can detect them. But the idea is that if the same physics that gave rise to the fluctuations that gave us our galaxies was somehow turned up at very small scales, so small that they're maybe even planet scale or even smaller than that, maybe they could have collapsed into a black hole. And there are ways in which we can go looking for them, and there's ways we could try to bound them. And this is an ongoing process. This is what the community is actually actively doing right now. And so the take home is that perhaps what LIGO has seen are in fact primordial black holes. And if that is true, that is telling us something very, very deep about the mechanism that gave rise to the structure that we saw. In fact, it's telling us something very deep about the thing that even gave rise to the Big Bang itself. So it's a very exciting question, but we need more evidence before we actually conclusively conclude that this is in fact what we've seen. And I don't know if you've been following the news, but over the last couple of years, but there's evidence that there's an object somewhere, outside the Kuiper belt, which is perturbing the orbits of, the outer planets and some of the objects in the trans-Neptunian objects, in such a manner that it looks like that there's a mysterious planet that we can't see somewhere, beyond Pluto. And so people have wondered, could that object, the reason we haven't seen it is that in fact it is a primordial black hole. And if it is a primordial black hole, in fact, it would be the size of a grapefruit. It would be something that's you actually hold into your hands, and it would exert as much gravitational influence as an actual planetary object. And so so these are this is if you like, it's a quick. I just gave a brief overview of the field and all the different questions that people are asking. And so I thought I'd just conclude the talk with sort of the open questions, maybe questions that you one day could yourself be a part of helping us understand. Is if we really want to understand whether these black holes that we're seeing in LIGO are primordial or astrophysical, we really need to determine the spin of the object that's colliding. And so if there's evidence, so if there's evidence that it had no spin, I think that's fairly strong evidence that it's very hard to make these guys from astrophysical processes. So that's something that people interested in gravitational wave research themselves might want to think about in the future. Another open question is, do these enhanced primordial perturbations make sense from a fundamental physics perspective? Because the origins of structure that we see in our universe ultimately have their origins in fundamental physics, beyond the standard model of particle physics. Maybe string theory, maybe some theory that goes beyond it. We don't know yet. So do these enhanced primordial perturbations even make sense from this fundamental physics point of view? Because in fundamental physics, things like to run weakly, logarithmically with scale if everything tends to be under control, or nothing drastic seems to happen. So how can we actually get this to realize this within our theories? Are there ways to make primordial black holes that we haven't yet even thought about? That's always a possibility. Are there clever ways to constrain their presence that we haven't thought about yet? And I think the most important question for me is there any way to kill this idea? So the way science actually works quite often, theoretical sciences in particular, is that we see some unexplained facts, then somebody comes up with a model that could try and explain for it, but we then have to look for evidence for this model. So in the absence of any direct observational evidence, maybe there's a way just by logic alone to kill this idea, or maybe there's some observation you could propose that if we saw it, it would kill this idea. So science often progresses by killing ideas, right? And I think one of the ways, let's say for dark matter, for instance, is people thought it was a particle, but the most likely candidate for the types of particles that could have been dark matter are these types of objects called weakly interacting massive particles, or WIMPs. It's just a type of model that comes quite naturally within particle physics, and of course, when people have gone looking for them, they haven't found them. So that idea is getting more and more into trouble, and so that's information, right? That idea is starting to look less and less convincing. And so it's equally meaningful in science to try and kill an idea as it is to try and invent something. And so these are all the open questions, and there's lots of astrophysicists and cosmologists still puzzling over this, and that's all I had to present on. So thank you for your attention.
Thanks, sir, for your nice presentation, and I think the students have learned a lot of things. So we have got some questions. So if we allow, we can start to read.
Yeah, absolutely. Go ahead.
So the first question, how the black holes are formed beyond degeneracy pressure, violating Pauli exclusion principle, and how particles can be
so that's precisely the black hole. So okay, so what is inside a black hole? We don't know. It's a complete, if you like, a rupture in space time, and our equations break down there. The point of Pauli degeneracy is precisely is precisely what neutron stars are, right? So if you like, neutron stars themselves can only exist up to a certain mass consistent with Pauli degeneracy before, if you like, they would end up collapsing into their own black hole. So there's a limit to which Pauli degeneracy can provide a force that can resist the gravitational collapse, and beyond that, we say the object forms a black hole. So how can some matter, go beyond that? I mean, it's the point is we don't know, right? We don't know what's inside of a black hole. The way to think about it is that your laws of physics break down at that point. Okay, so we have a locus through which we don't understand what's going on. I mean, the deeper theory, which we don't have yet.
Thank you, sir. So we have another question in the inbox. So is it possible to form black hole in the lab?
That's a very good question, and the answer is it depends on some things. So if the laws of physics are as we know they are, then well, in principle, yes, if your laboratory was a particle collider the size of our galaxy, right? So if your question is by laboratory, do you mean something we have on the Earth? The answer is, if the laws of physics are as we think they are, no. But it could be that, in fact, the fundamental scale of quantum gravity is much lower than we think. And there's a variety of scenarios in string theory and beyond the standard model physics that can cause that to happen. So gravitational processes become important when you get to energies approaching, if you like, m Planck. Okay, so that's 10 to the 18 GeV, giga electron volts. To put that into context, the Large Hadron Collider can only go up to 10 to the 3, approximately 10 to the 3 or 10 to the 4 giga electron volts. So still 14 orders of magnitude away from any energy where, you know, the physics responsible for producing strong gravitational effects is being reached. But there are models in which, in fact, the scale at which that happens is much, much lower. Now, if that were true, then a big enough particle accelerator could detect it. And that is something that people entertained about 20 years ago. But I think that idea has been pretty conclusively ruled out in terms of the energies that we see in the colliders we've made, which isn't to say that it might not be just above the scale at which we look. So the question is, so the answer to your question is, yes, it's possible, but it would need to invoke physics that is beyond what we understand today. And that would be spectacular evidence of physics beyond what we understand as standard general relativity.
Thank you, sir, for your answer. So we have another question. So is there no fluctuation of matter distribution in the early universe? So then what happened? If there is no fluctuation of matter distribution in the early universe, then what happened?
So well, let's first answer that question in terms of the universe we live in, and then we'll answer that question in the universe we don't live in. So in the universe we live in, that's impossible, right? Because quantum mechanics will always give you fluctuations. There's always going to be fluctuations in everything. Okay, quantum mechanics is not a theory; it's a physical requirement that all physical theories have to satisfy. Okay, so it's like asking the question, can I stand a pencil on end forever? Right? The answer is no, you cannot, right? Because even though you think you might be able to have a pencil stand on end by tuning its initial conditions so precisely, eventually you'll violate the Heisenberg uncertainty relation. And there's going to be a slight fluctuation that's always going to be because of 0-point motion. And in fact, it's a very interesting exercise to work out that an experiment you can do with your own, on a tabletop. The actual quantum mechanical limits to how long a pencil can stand on its end is about 10 seconds. Okay, so that's an experiment you become an order of magnitude within to quantum mechanics. So there's no way things can't have fluctuation. There will always be some fluctuation. But to answer the question, imagine h bar was 0, and we could imagine a universe with no fluctuations. Then we wouldn't be here to talk about it. Nothing would have formed.
Thank you for your answer. So we have another question. So can we detect Hawking's radiation of primordial black holes?
So can we detect them? It depends what you mean by detect. But so in fact, one of the ways in which we rule out primordial black holes of a particular form is precisely because of the Hawking radiation. So if you imagine there was a population of primordial black holes that were really, really so light that they were evaporating very strongly into the primordial plasma. Then what that would have done is would have injected lots of energy into the primordial plasma in such a way that we would have distorted the spectrum from being a perfect black body to something else. So, and we don't see any evidence for that. So yes. So in principle, were there primordial black holes that were Hawking evaporating, we could potentially see them in distortions of the cosmic microwave background spectrum. We haven't seen it, but maybe we will one day with accurate enough measurements. For Hawking radiation of much, much larger black holes, it's just so weak in intensity, and it's just basically impossible. It's below the thresh sensitivity of any experiment that we have right now or in the foreseeable future. But it remains a possibility that they could have happened in the early universe. And in fact, people do use that to rule out black holes below a certain mass because they would have produced too much Hawking evaporation.
Thank you, sir. So we have another question. How can we connect black holes with inflation?
Yeah, so this is in fact the idea that I was trying to flesh out is the way in which these fluctuations at very, very small scales could be enhanced. There are ways in which you can do that through inflation. And so in fact, people think that inflation is in fact the thing that is responsible for creating these primordial black holes, because at scales that we see at the largest scales, so in this cosmic microwave background and the structure of the galaxies, the inflaton field, the inflation field has a 2-point correlation function that's basically scale free. But then, once you look at very, very small scale Fourier components, it really goes up. It really goes up. And there's ways to get that inflation in inflation. So if you imagine inflation being because of a scalar field rather than a potential, every time it hits an inflection point, it'll do that very briefly. So yes, so in fact, that is part of the game that a lot of theorists are playing, is that they're actually saying inflation is responsible for this enhanced primordial structure. But it's by no means the only way to do it too. So how do we tell those two possibilities apart? It's an ongoing enterprise. But to answer your question, yes, people do think inflation is the mechanism that's responsible for enhancing structure at small scales.
Thank you, sir. We have another question. So, primordial perturbation were enough massive to form black holes?
Yeah. So the thing is, I think the thing to understand is, um, um, black holes don't need matter to form, right? I think that's the thing I was trying to get at, right? So one thing you could do, for instance, is take two gravitational waves, no matter, of very high energy, and smash them together, and then in the shock waves that result because of nonlinearities, you will form. You can in principle form black holes if they are sufficiently energetic. So primordial perturbations, what they're doing is they exist, right? And these fluctuations can be so big that, if you like, once they re-enter the horizon, if you like those perturbations are so big that if you like, the matter content that has fallen into it is so big that it's within its own Schwarzschild radius and it forms a black hole. That's exactly the idea of how it works, is that the fluctuations of spacetime itself are so big that they collapse into a black hole.
So thank you, sir. So we have another question. So what is the identification of black hole?
Excuse me. So how do we identify a black hole?
Yeah.
I mean, so we've been seeing black holes indirectly for decades, right? And I think the most direct evidence, if you like, of what we've seen as a black hole is this picture by the Einstein Hubble telescope that just happened a few years ago, right? I mean, by definition, it's an object you can't see. But we've seen at this point, evidence that it exists in gravitational waves and in electromagnetism. This year's Nobel Prize, for instance, was given to people that saw that the thing that's existing at the center of our Milky Way, if you look at the orbits of stars, they're orbiting such that the thing that exists has to pack so much matter in that it could only be a black hole. So the question is, how can we tell whether it's a black hole or if it's not? Well, it's the only object that could cause the behavior of some of the things that we're seeing. But I would say that if you like, the smoking gun evidence is this Einstein Hubble telescope image, which perfectly fits the predictions of GR in the optical.
Thank you. So we have another question. So did dark matter has any role during formation of primordial black hole?
At this point, you don't need, not necessarily, right? So dark matter is in principle a separate topic, but the idea is that maybe primordial black holes themselves are dark matter. That was the idea, right? But it could also be that there's primordial black holes and dark matter around. But in terms of the effects of dark matter on the formation of primordial black holes, dark matter only comes in much later in its effect of how the universe evolves, right? It only comes in after, if you like, matter domination, which happens much later in the history of the universe than the times that we're talking about, when these black holes are potentially formed. It's happening deep within radiation domination, when the very early universe, where matter is a very subdominant component. It's almost as if it weren't there. But it's beginning to fall into these gravitational potentials, which is causing what we're eventually seeing in the cosmic microwave background. But in terms of the mechanism to form these primordial black holes, it's a completely separate thing.
So thank you, sir. We have another question. So how quantum gravity comes within the black holes?
That's a good question. I don't have the answer. I don't think anybody does, right? So we don't understand. We don't understand the physics of black holes until we understand, like, really, we will never understand really what Hawking, what the end state of Hawking evaporation is until we understand quantum gravity. And this is a theory we have guesses. We have very good guesses, but we don't really have a convincing theory of that one could come up with unambiguous answers to your question.
Okay, so thank you, sir. We have another question. So why does the fluctuation happen, and what physical properties is responsible for this fluctuation?
Yeah, it's quantum fluctuations, right? So these fluctuations are quantum. The origins of these fluctuations are quantum fluctuations in whatever field it was that gave you inflation, right? You can't have anything without nothing. Everything fluctuates in this universe at the very smallest scales, right? At the very low energies. It's just quantum 0-point fluctuations.
Thank you, sir. So we have another question. So how relic densities arises?
So that's a question more of the standard thermal history of the Big Bang, and relic densities arise simply because the universe begins. Everything is in thermal equilibrium at one point, and then at some point, the interactions become too weak to maintain thermal equilibrium, and the field and once thermal equilibrium is no longer maintained, if you like, that's the objects just sort of freeze in. They're just sort of there, and then they just redshift according to whether they decoupled when either radiation or whether they decoupled when they were matter. So that's a standard thing you can look up in a textbook about Big Bang cosmology. But that's how relics exist. Is that the idea is that the Big Bang was so energetic that everything that can exist does exist, right? And even if it didn't, quantum mechanics, the virtual processes would create it. And as provided that interactions are strong enough to maintain equilibrium, so equilibrium requires interactions. Then they're just sort of moving along with the universe adiabatically in terms of as if they're in thermal equilibrium. Once your interactions switch off, then they just sort of remain frozen there forever. Those are your relics from the Big Bang.
Thanks, sir, for your answer. So we have the last question. So if we consider primordial black holes are still present, then can we detect gravitational wave of merger of them today?
Yeah, so in fact, that is precisely the motivation for why people started thinking about primordial black holes. Is that people thought that the very first observation that LIGO had was primordial black holes, right? I mean, that's the idea, right? And the reason is because the masses that LIGO had seen are very hard to produce through stellar collapse, through astrophysical processes, right? So LIGO saw something of order 39, 29, and 36 solar masses merging. These are masses that are very strange from the perspective of astrophysics. So people thought that maybe these are primordial. And so how can you tell whether they're definitely primordial versus not maybe produced by astrophysics? Then I think then you need to ask, can we detect the spins of these guys? So if the spins of these guys were consistent with zero, or we can actually tell that they were zero, then it's very strong evidence that indeed they were primordial.
So thank you, sir. We should conclude our discussion as we don't have any more questions. So thanks again, and we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. So I think students have learned a lot of things about primordial black holes. So we say actually this is a very good webinar with you, sir. And if you have a time in near future, we'll arrange another exciting webinar with you. So thanks again, sir. So so our students have learned a lot of things by your webinar, sir. So thanks again, sir.
Thank you very much.
Bye for today, sir. Bye.